Hello everyone, my name is Kathan and today we will be discussing the problem array division from the sorting and searching problems of the CSES problem set. Let's begin. Let me read out the question for you. You are given an array of n positive integers, so we have an array of n positive integers. This is important. Your task is to divide the array into k subarrays so that the maximum sum in a subarray is as small as possible. Right, so we have to split our subarray into k parts and the maximum sum among all the subarrays is as small as possible. Okay, and if you see the input here, we are simply given in the first line in two integers n and k. N represents the size of array and k represents the number of divisions that you have to do, right? Or you can the number of splits that you have to do. The next line contains an integers, which is simply the array value, and the output you have to print one integer, the maximum sum in the subarray in the optimal division. So what this is asking is, you are given a array of size n, which has all positive integers, and you want to split it into k parts, and you want to split it into k parts in such a way that you split all of them, right? And let's say individual split sum is si. This max of all the subarray sums should be as less as possible, right? So max of s1, s2, s3, so on till k, because we'll have k splits. So this maximum sum in a subarray should be minimized, right? So maximum among all the splits should be minimized. And yeah, we'll touch upon the constraints and example test case in a bit, but I guess that's the question. You are given an array of n positive integers, you split it into k parts such that if I take the maximum of sum among all the splits, this should be as less as possible. Let's go to the iPad and discuss this question a bit more. So what this question is trying to ask is, you are given an array of size n, right, and you want to divide it into k parts. So let's just call this as k part. So this is first part, second part, so on. We want k parts here, right? So all in all, there are k parts here, and let me call the sums of these individual subarrays be s1, s2, s3, and the last guy to be sk, right? So what we want to do is we want to split this array into k parts or k subarrays in a way that you can say we want to minimize the max of s1, s2, s3, so on till sk, right? So you devise a split, right? So you decide how many elements you're going to put in each split such that the maximum of s1, s2, so on till sk is minimized, right? So you don't tell me the splits, don't tell me this k subarrays, you just tell me what is the maximum sum of this s1, s2, sk, which is as less as possible. You tell me the max of si, optimal value of max of si. What is the optimal value of max of si? The smallest possible max of si, right? So the output should be smallest possible max of si, and where this I belongs to 1 to k, because you want to divide your array into k subarrays, right? So that's one thing. So let's talk about constraints here then. N was greater than equals to 1 and less than 10 power 5, and k was less than equals to, and obviously, like if you have, let's say, array of size 3, the best case, you can say in the worst case also, you will do only 3 splits. You will divide it into 3 parts, right? So that's one interesting thing. And individual array values were less than equals to 10 power 9 and all, so fine. So if you want to do some sum and all operations, we may have to take care of overflow. That's one thing. Now what does this say? If we are talking about time complexity in terms of n or even k, you cannot devise a solution which is order of n square or order of n into k, right? Because this is going to consume what? 10 power 10 operations, which are definitely higher than 10 power 8. So in 1 second, you cannot do more than 10 power 8 operations. Okay, so if you cannot do this, then we definitely have to think about n log n, k log k, or n log k, so on and so forth, right? So we have to do something better than this. Okay, so with that clear, let's try to understand this question from an example test case. So the example test case, I'll take the same one. N was 5 and k is 3. So n5 means we have 5 elements. So array contains only positive elements. Okay, so that's one thing. So the 5 elements were like this: 2, 4, 7, 3, and 5. So one way to split this, you can say, array into 3 parts is this, right? So you have split this array into 3 parts. But what is the maximum sum, right, among all the subarrays? So here the sum is 2, here the sum is 4, but here the sum is what? 7 plus 3, 10 plus 15. So max of si here is 15. Okay, but is there another split existing? Is there another split of 3 subarrays existing which yields a sum less than 15? Let's see. What if I divide the array into 3 parts like this? So here now the sum is 6, here now the sum is 7, and here now the sum is 8. So what is the max of Si here? Max of Si is 8. And this is indeed the optimal split. You cannot split this array into 3 parts in any other way, such a way that the max of Si is less than 8. You can try it. So here you have to print actually 8. Right? So you want to devise a optimal split of k parts such that max of Si is minimized. Right? So with the question being clear, let's try to approach this question. One thing is clear here, you cannot sort the array. Why? Because the splits happen sequentially. So the first part will contain first few elements, the second part will contain another few elements in order, right? So sorting is out of the picture. You cannot do sorting here. Alright. So if that is not possible, let's try to bound our answer. So what do we want to minimize? We want to minimize this value, max of Si, right? The maximum sum should be as less as possible. So forget about max of Si. Let's just see where this Si can lie, right? If we can figure out where Si can lie, maybe we can get some idea. Okay. So what is the minimum possible value of sum, like among the parts? So if I have, let's say n is 1 and k is also 1. We only have to do one split, and the x1 value is also 1. So we just have this array. So in this case, you can say the minimum possible value of sum can be simply 1, right? So you only have one split, and that has sum 1. So here the answer would be 1. Okay, fine. Then what can be the maximum value of split? Let's say n is n, and k is 1. We only have to do one split. And x1 till xi, like x1 till xn, you have some values. So in a way, you have an array here. Okay. So in this case, what will be the sum? You can say what will be the sum. So here the sum will be what? Simply summation of xi, sum of all the elements, right? So in this case, this is our answer, right? So the max sum that can be our answer is simply summation of all elements, because here you only want one split. In other words, you only want one part. So this is one part. And what is the answer here? The max of Si is simply summation of all elements. So in other words, we know that this, you can say, what do you know about Xi? This Xi is as high as 10 power 9, right? So the summation of Xi will be what? 10 power 9. And what is the size of, you can say, our array at the worst case? It can be something around 10 power 5. So all in all, the maximum sum can be 10 power 14. In other words, our answer, the minimum value of max of Si, lies in this range, 1 to something like 10 power 14. Or maybe let's just increase a bit, because I guess it was 2 into 10 power 5, right, the array size. So it is fair to say that our maximum answer lies in range 1 to 10 power 14 or 10 power 18. Okay, I know it's less than 10 power 18, but it's safe to say that my answer lies in this range, the S value, right? The max of Si value lies somewhere here. Okay, now what? Now my question to you is, if I give you some sum in this range, let's call this as S dash, can I verify uh, if a split of k subarrays possible? Can I do that? So we know that our sum lies in this range, right? So our answer lies in this range, 1 to 10 power 18. If I give you some any random sum S dash in this range, can you verify if a split of k subarray is possible? Let's see if we can do that. So what we will need is, let's say this is our array. Now we have a sum, let's call it S dash. We want to see if we can get k subarrays out of it, such that maximum sum doesn't exceed this S dash. So you can adopt a simple strategy. What you can do is, you can start from left, and whenever sum is exceeding S dash, you can make a split. So all the elements in this portion, sum is less than equals to S dash. Again, you can continue a journey. If the sum is exceeding S dash, you increment the split count. Similarly, you keep on going, and eventually you will get some splits, right? So let's say you got some splits, right? Such a way that all the sums here are less than equals to S dash. So this you can easily do, right? You can write a order of n loop, which makes one pass through the array, and whenever the sum is exceeding S dash, you can make a split. Now let me call this as number of splits. Okay, so however number of splits you get here, Now, if this number of splits is greater than k, it means to make sure that the sum is not exceeding s dash, you are requiring more than k splits. It definitely says that you cannot have k splits, you can say k parts of an array with sum not exceeding s dash. In other words, if number of splits here that you do in this strategy is greater than k, then answer is false. Right? Then answer is false. But if the number of splits that you are doing this strategy, that strategy is going from left to right, and whenever the sum is exceeding s dash, you create a new split out of it. If it is less than equals to k, then yes, you can definitely have k splits of your subarray, k split of your array, such a way that the individual subarray sum is not exceeding s dash. How? See, if you have 3 splits where the sum is not exceeding s dash, we can also have 4 splits, right? You know for the fact that in this portion the sum was not exceeding s dash. So even if you do one more split, definitely in these two portions also the sum won't exceed s dash because all the array elements are positive, right? And so this actually directly follows from the fact that all the array elements are positive, right? So it means that if you have a subarray whose sum is not exceeding s dash, even if you split it, you know for the fact that the new parts that you will get, their sum will also not exceed s dash. So if number of splits that you are getting is less than equals to k, we can definitely have k splits. And we also know for the fact that k is less than equals to n. Right. So in the worst case, let's say the number of splits that you get using this strategy are n minus 1. Right. So if this was the array, let's say 4 elements. So if this was the number of splits you were getting, now if let's say k was n minus 1, right? So if you can get 3 splits, so you can definitely get 4 splits as well, right? You can definitely get 4 splits as well. So what I'm saying is, guys, let's say k was n. You had to do n splits, and using this strategy, you are ensuring that the sum here is not exceeding s dash. Sum here is not exceeding s dash. If you can get 3 splits, you can definitely get 4 splits. That's the idea, right? So yeah, there is a way to find out whether you give me a sum s dash, whether you can get k splits or not, and this actually consumes just order of n time. Okay. One more important thing is if we can get k parts, you can say k splits, that is, I can divide it into k parts such that sum is less than equals to some s dash, we can also have k splits such that for all sum greater than s dash. That's obvious, right? So if you know for the fact that in this k splits the individual sums are not exceeding some s dash, then definitely these sums are not exceeding any number greater than s dash, right? So that's obvious. So what does this lead to then? We know for the fact that our answer lies in this range, 1 and 10 power 18. And we can definitely not create, you can say we cannot definitely have splits with certain sums. But after a while, let's say for this s dash, we can create a split in a way that we have k parts and the sums are not exceeding s dash. Then after all the sums after s dash, we can also create the split, right? So if I define, you can say a monotonic function here, if I define a function here, can make split with the sum s dash. What is the property of this function? For some sums, it will return false, right? That is, I cannot create k splits with this sum, right? I'll need more splits. But after a while, if we can create after a while, if we can create k splits, let's say at this sum, the smallest sum, we can create a k split such that sum is not exceeding s dash. We can also create k splits after every sum afterwards, right? So what is this function? Do you recall the that problem, factory machines? This is a monotonic predicate function. So why do I call it monotonic predicate function? See, it is predicate function because this function, given a sum s, returns true or false, whether I can create k splits or not, right? And it is monotonic because it is all false followed by all trues, or it may be very well might be all trues followed by all false. So if you have such functions, these are called monotonic predicate functions, and you can easily do something called as a binary search on answer on monotonic predicate functions. So more concretely, if I want to define it, if you are given a monotonic predicate function, here we have f of s dash, right? So it returns true when we can create k splits using some s dash, or false if we cannot create k splits. You can definitely do a binary search on this answer space where it is all falses followed by all trues to find the first t, in such a way that this t, what is this t corresponding to? This t is corresponding to smallest maximum sum. It is corresponding to the smallest maximum sum such that we can do k splits, right? So that's what you can do. So if you want to talk about like what is the time complexity for this, we can do a binary search on this search space. So order of log 10 power 18 for the binary search, and to check whether the value of this function is true or false, we'll need order of n. So log of 10 power 18 into order of n. So order of n is what? So this entire value turns out to be log 10 power 18 is 60, and 60 into 10 power 5. This value is less than 10 power 18, 10 power 8. So we can definitely do optimally, and this will not cause TLE, right? So that is the approach. Let me write a pseudocode for this, so then you will understand it a bit better. Let me write the pseudocode here, but before that, let's define our objective. We have a monotonic predicate function f of s dash, which returns false. So which returns false for some sums at the start of the search space, and afterwards it starts returning true. And what we are after is, you find me the s dash corresponding to the first t. You find me the smallest max of si, which can give me k splits, right? So what I'll do is I'll initialize two variables, my binary search endpoints. Low is 1 and high is, you can either initialize to max of like summation of xi also, but since we know that it will anyway not exceed 10 power 18, I can initialize like 10 power 18, right? So high is basically the largest possible value of our answer, which here is 10 power 18. Fine. Then what I'll do is the normal binary search loop, while low is less than equals to high, you calculate the mid. So you calculate the candidate s dash, right? So you want to check whether I can create k splits using this sum, low plus high divided by 2. Now you need to call this function, this f, right? So can I make k splits using this sum s dash equals to mid? Can I do that? So if I can do that, if this function returns true, it means I am somewhere in this part. If I'm somewhere in this part, it means I have to discard the right half and only search in this direction, because I'm after the first t, right? If I'm in this half, so you know that there are a lot of t's afterwards, right? So there are a lot of falses. So your mid, if your mid lies somewhere here, you can happily discard the portion afterwards and search in the left portion, right? So here, what you can do is, you can make high equals to mid minus 1. But it very well might be the case that the mid is exactly pointing to the first t. So you also update the answer, right? So you also update the answer to mid, right? You do this because you want to discard the space afterwards, the right half, because there is no point in looking there, because all are t's anyway, right? Okay. Else, if you cannot make k splits, then you're definitely in this part. If you're in this part, let's say you're at this f, then there is no point in looking in the left part, right? So this part, everything here is false. So we simply do low equals to mid plus 1, right? So yeah, I mean, after this binary search ends, like if you are here, your search space will be reduced, then you'll search here. If you are here, then the search will be reduced, then you'll search here. And eventually answer will be updated to the first t. You can say the input corresponding to the first t. You will get the smallest max of si, right? You will get smallest max of si, right? Such that you can generate k splits. Fine. Now all that remains is to define this can make. Now this is a very simple function. It simply checks whether I can create k splits or not. So this is a boolean function, and let me define it, can make, and it takes the input sum. Let's just call it sum s dash. So we want to check if I can create k splits such that individual sums are not exceeding this sum s. So let me define splits here to be equal to 0. Then what I'll do is I'll define my, you can say, accumulated sum for a current part to be 0. And what I'll do is I'll go through individual array elements for a in ARR. Okay. The first thing is, if this a itself is greater than s, then you can definitely not have, you can say, k splits with individual sums not exceeding s, because if individual value is greater than s, then it doesn't, you can definitely not have it. So here you have to return false. So here you return false. Okay, fine. Otherwise, you need to check, can I include the current element into this part? So in other words, if a plus the current sum that you have, the current part sum that you are trying to extend, if this is not exceeding s, if this is less than equals to s, then it is great. You very well include it. Sum plus equals to a. Okay. So you have some elements in your current part. If you can include this guy so that the maximum sum is still not exceeding s, yeah, very well include it. But if it is exceeding, the maximum sum allowed, then we have to increase the splits. We have to increase the splits. And sum changes to a, right? So for example, if we have these two guys and you're trying to include this another guy, and it is increasing the total sum, then we have to make a split. And now for the next part, initial sum is equal to this guy, right? So sum equals to a. And all that remains is, after this function ends, you simply check if the number of splits is less than equals to k or not, right? If the number of splits is less than equals to k, we can definitely make k splits. In this case, returns true, otherwise returns false, right? So in other words, I can simply write return splits less than equals to k, right? Because if you need more than k splits, definitely answer is false. You cannot make k splits as the individual sum is not exceeding s. But if number of splits required are less, you can definitely do more splits, right? If you can do here 2 splits, you can definitely do 3 splits. That's one thing. So yeah, with that thing clear, like, so we have so that actually wraps up the pseudocode, right? So let me zoom in a bit. So yeah, that's the pseudocode for you. We simply do the binary search on answer space, and we find the smallest s, smallest, you can say, maximum si, using which you can do k splits. That is, we want the first t in a monotonic predicate function. So yeah, I mean, that's for the pseudocode. So I hope you understood the explanation. If you did, please comment understood in the comment section of the video, and let's look at the code and wrap up this video. So before we move ahead, I noticed one little thing which is wrong, which is the number of splits in this can make function should start from 1, right? So you will initially start adding elements in the first part. So initially the number of splits will start from 1, and if you can include a current guy in the sum, you are going to add it. Otherwise, you create a new split. So that was a little thing, right? So I hope many of you may have noticed it. We start our split count from 1, and if an element cannot be included, we create a new split. If it can be included, we include it. But if the current element is greater than s, then we anyway directly return false from that. So yeah, that's one little thing. Now let's move to the code and wrap up this video. Alright, so here's the code. First things first, we take the input n and k, n being the size of array and k being the parts that we want, right? So we want to divide our array into k parts. Then I'll take the array input. Notice I'm taking the integers, or you can say every integer values here as long, because for simple reason that we have to do some sums, right? So we don't want to cause overflow, right? That's why I'm taking everything as long. Okay, and then we know our search space is defined by a monotonic predicate function, which returns all falses followed by all trues, and we want to find the first t. more precisely, we want to find the sum corresponding to this first t. Now, low is 1 and high is, notice, I'm actually doing it sum of all the array elements. But here you can happily do 10 power 18, that also works. So I've just written it because I wanted to explain you that I know that the maximum value for our answer is simply sum of all the array elements, right? This is when k is equal to 1. Okay, then we initialize answer. Since we want the smallest possible sum, I'm initializing answer to the high, right? As big value as possible. Then this is our normal binary search loop, and then we find out the mid. Notice how I find the mid. I do low plus high minus low by 2 to avoid overflow. Because if you directly do low plus high by 2, and if you are in some order of 10 power 18, it will cause an overflow for long as well. But this formula ensures that your mid, like you can say when you do the calculation, it doesn't cause overflow, and you always stay in the range of 1 to 10 power 18. Right, so this mid is nothing but your candidate sum that you want to check. That is, now I want to check whether you are in this half or you are in this half. Right? If you can create k splits, it means you are in this half. That is, if you are in this half, let's say you are at this t, then you discard the entire portion towards the right of it. That is, you do high equals to mid minus 1. But it very well might be the case they are at the first t. So please update the answer. Then try creating with a lesser sum, right? So if you are in this, if you are at this t, now go search in the left half, right? Go search in the left half for the first t. Try lesser sum. But else, so if you cannot create k splits, it means you are in this portion. So let's say you are at this f. Then there is no point in looking towards, you can say, on its left. So simply do low equals to mid plus 1, and we don't update the answer here, right? So after this loop ends, we will have our answer updated to the smallest s, which yields t here, right? So we'll find the smallest t, and we can print the answer. And we already know the time complexity here is n log m being the search space, which is 10 power 18. So this value is less than 10 power 8. So it works without giving any TLE. And space complexity here is order of 1 because we are not using any extra space. Now all that remains is to check whether I can create k splits using this sum. Let's just look at this function then. So what this function checks is whether k subarrays with maximum sum target is possible or not. So this is the sum that we don't want to exceed. So what we do is we initialize our count to 1 because we know that we will have, you can say, in the worst case, at least one part, right? So I guess in the pseudocode, I initialize it to 1, 0, right? So I guess that was a little bit mishap from my end, but this should be initialized to 1. And then this is a sum of, you can say, current part. Then I go through the array. If the array element itself is greater than target, we can definitely not have k subarrays such that individual sums are not exceeding the target. So in this case, return false. Then check, can I include this array in the current part? Include this array element in the current part? If yes, if yes, then we increment the sum. Otherwise, we create a new part. That is, we do count plus plus and sum equals to v of I. Right? And then after this loop ends, now we have the split count. If the split count is less than equals to k, we definitely can create k subarrays. But if it is greater than k, we cannot do it. So we return count less than equals to k. So yeah, I mean, that's about the code, guys. So, and that was the video. So if you did find this video helpful and you learned something new, please give it a thumbs up, and I'll see you in the next one.